this might seem complicated. It's not as bad as you think. So basically what I'm trying to illustrate here is that now that we know how to differentiate sine and cosine, we can just use the rules of differentiation to find the derivatives of all the other trigonometric functions, right? Because we can express the tangent function, the cotangent, the secant, and the cosecant in terms of sine and cosine. So remember that the tangent function was just sine over cosine, agree? So if we want to differentiate tangent function, we should just differentiate sine of x over cosine of x. And last time we looked at how to differentiate functions that are written as fractions of two other functions, right? So the rule was that first we differentiate the function on top, that gives us ddx of sine of x. On this page I will write ddx instead of primes because it might look strange for sine and cosine. Then we should multiply by the function we have at the bottom, that gives us this. Then we should subtract the function we have on top times the function we have below differentiated, so ddx cosine x. And then we should divide everything by the function we had at the bottom squared, so that gives us cosine squared at the bottom. Now from a bit ago we learned that the derivative of sine was cosine and that the derivative of cosine was minus sine. So we have now cosine of x minus sine of x times minus sinus x over cosine squared of x. Now these two minuses cancel, so we can rewrite this as cosine squared of x plus sine squared of x over cosine squared of x. Now we had this fundamental identity of trigonometry, which tells us that the square of cosine plus the square of sine is always 1. That's just the fact that comes from the fact that if you look at the unit circle and draw a triangle, right triangle, then we will have that the hypotenuse has length 1, right? So the square of these two will be 1. The cosine squared is still there. Now I've written this as 1 over cosine x. This is what we have here. I also claim that it can be written as the secant squared. Now why is that? Well, it's because the secant was just 1 over cosine. So if we square this, we get 1 squared over cosine squared, which is this. So these two are identical just for algebraic reasons. And another way of writing it is this. To get this expression for the derivative of tangent, it's better to look at this, because now we can see that if we split this fraction in two, there are two terms on top, right? Then we have a cosine squared of x over cosine squared of x. What is that? Well, it's 1, right? If we differentiate something with itself, it's 1. And the other part is sine squared over cosine squared. But sine over cosine is tangent, so sine squared over cosine squared is tangent squared. So that gives us this. So in other words, we can, for good reasons, write the derivative of tangent x in 3 different ways. We could have done something completely similarly for the derivative of cotangent. Basically, all we should do is replace any sine here by cosine, and vice versa, right? Because that's how the cotangent could be written in terms of sine and cosine. We could have done something similar for the secant. It had a different definition, but it was just based on one of the functions, sine and cosine, and the same was true for the cosecant. We're not going through these either. Maybe if you want to see them, I can do it on the blackboard later. So just to indicate that this makes sense, I've drawn the tangent function here and the why can't I grab that here? and the 1 over cosine squared of x here. So does it seem reasonable or look reasonable that this function here is the derivative of this? This is also a way of testing your own intuition of how these things work. So when you differentiate stuff, you get the slope of the function, right? Here we have a very steep function, right? It's extremely steep at this point. So we would expect that the slope is a big number. Clearly it's a big number. But it's becoming less and less steep here, right? So the slope should decrease. It clearly decreases. At some point here, there's a turning point. It has decreased for quite some time. Now it starts increasing again. This means that we should have a sort of bottom here, minimum, local minimum. And the slope here, I mean, you can't really see it, but it seems reasonable that this slope here is 1, right? And in fact, you will see that the minimum of this function here is exactly 1. So the minimum is 1. Then things start to increase again, and the same happens here. And another thing you can notice that the way that this function looks like here is basically a rotation of how it looks here, right? So the slope, say here, is exactly the same as the slope here. This means that the slope here should be the same as the slope here. So you can mirror them. So it looks reasonable.